All right. So let's get started. Welcome everybody to the introduction to HPC UGent. Let's start with a question. I'll be asking many questions, so I'll try to keep you awake. Who has never submitted a job on the HPC clusters before? Okay, about half the people. Who has submitted more than one job? More than 10? More than 100? More than 1,000? All right, we have a winner. Yeah. Okay. So everybody's welcome. This is an introduction, but if you're totally new, that's fine. If you have some experience, that's also fine, and hopefully you'll learn some new stuff. Yeah, if there's another guest account, we can do it during lunch. Yeah, during the session, you don't need actual access, but for the hands-on this afternoon, that will be useful. Okay, so the agenda for today, we'll start with the lecture part, about 2 hours, starting from scratch, explaining everything, giving an overview of the hardware we have, how to get the VSE account, which you probably already have, how to use the system, how to get help, and do some live demos and examples. If all goes well, we'll end around noon to have lunch. And then shortly after lunch, we'll do a guided tour of the data center, which is just across the parking lot here, so it's very close. And then the afternoon, which is optional, is the hands-on session. So there, the plan is that you get started either from scratch with the examples that we gave you, or with your own software, with your own research, take your first steps. Or if you're already beyond that, we'll be here to answer your questions. If you have more deep questions or more advanced questions, those are definitely welcome as well. Just again, the hands-on session is optional. If you stay, that's fine until 5. If you run away at 3, we will not ask any questions. So you're free to leave at any point during the hands-on. Okay, so let's start with the lecture. First of all, an important point, we have documentation, quite a lot of it. Please read it, please check it. Please search for things. If you're unsure about something, it's quite possible that your answer is already in there. So docs.hpc.ugent.be will cover a big part of the documentation during today's lecture, but definitely not everything. There's way more detailed stuff in there, software-specific things, specific to certain use cases, troubleshooting parts, which we'll not go over in the slides, at least today. So please do check the documentation before you contact us for help, and I'll explain towards the end how that works. So who are we? HPC UGent, in a nutshell, we're part of the central IT department of Ghent University. So we cater to the whole university. Any research domain, any research group you are working in, we're happy to help you. And we even go beyond that. We also work on the Flemish level and even on a European level together with other HPC sites throughout Europe and even the world. So we focus on providing centralized services for scientific computing. We do training like we do today. We give support for researchers who want to use the infrastructure, not only from Ghent University, but also industry and other Flemish universities and knowledge institutes, research institutes, and so on. So the people behind how all this works is now actually split in 2 teams. It used to be one big team. It's now a bit more split. We have the HPC operations team. These are the people we hide in the basement. They don't deal well with people, so that's fine. They're very good with computers. Actually, Wouter may pop up during lunch. But yeah, these people you usually don't see, except maybe via email if there's any specific questions. The HPC support team, so that's us, me, Balázs, Lara, Ewald as the team lead, Gottfried also in the back there. And then we have 2 people who are working remote from Czech Republic, consultants who are helping us out with software installations. So what is HPC in a nutshell? That's for Lara, actually, yes.
Yeah, okay. I hope the people in the teams can also hear me. So yeah, what is high performance computing? So high performance computing is running computations on a supercomputer, very easily explained. So you can do a lot more stuff than on your simple desktop. You can do parallelization on the things and do a lot of bigger stuff. One of the terms that we'll be using today as well is a computer cluster. So a computer cluster is a bunch of computers connected together, which then give a lot of more possibilities to do bigger computing. We'll also talk about supercomputing and scientific computing, but yeah, that's all falls under the term of high performance computing. What does a supercomputer look like in the afternoon? For the people who are here, we'll see the actual computer that you do your compute here at the UGent. But yeah, in the 1944, one of the first supercomputers, or one of the first computers, was of course Colossus. And then in the 1985, you had the first supercomputer, which was the Cray 2 system in the middle. And then you also have some, still today you have some research groups that have their own makeshift supercomputer by connecting a bunch of desktop computers somewhere in the basement that you can see there on the pictures. And then here on the bottom, you see a picture of our supercomputer in 2018, and that's also the machine that we will see later today, or parts of it. In the middle, you see the IBM Blue Gene, which was the fastest and biggest supercomputer in the world at that time. And then you also have a picture from Mare Nostrum 4 in Barcelona to show that a supercomputer is not always housed in a data center in a white cube, but it can also be in a lovely space, such as the chapel at the University of Barcelona. Okay. So what can you do on a supercomputer? So we can do lots of stuff. You can do weather and climate prediction. You can do animation rendering, molecular dynamics, fluid dynamics, simulation of atomic weapons. So yeah, everything you need, you can do on a supercomputer. So some more terminology of a supercomputer. So we're also going to talk about worker nodes. So here you have like a visualization of one of our clusters, Doduo, which is a default cluster. So if you don't really know where you're at, if you're going to submit jobs and not really specify the cluster that you're on, you're going to land on Doduo. So a worker node is one of the cubes that you can see in the overview here. And so it's one computer, it's one server with about it's the one cube is one server, and they're all connected together. So in Dodio you have about 128 worker nodes, which are all connected for parallelization of things. Okay, yeah. So you can see the status of all the clusters here via this link if you want to see how many parts of the cluster are ops and are not. Some more terminology. So you also have cores, CPUs, and processors. So here in the visualization is like one worker node in the whole cluster. Most of the worker nodes today, they consist of 2 sockets. And in those sockets, you have then a bunch of cores, which are the gray little cubes. So if you're requesting resources on the cluster, you're going to request how many CPUs you want, how many worker nodes you want, and all that stuff. You'll also talk, I've already mentioned like parallel computing a little bit. So on a supercomputer, you can do either parallel computing or sequential computing. In most cases where you don't see any mention of the software being parallelized, you're going to be in the sequential. You're going to see a sequential software. So that means that the software that you're running will also only stick to one core and will do all the computations on one core. But to get then more use of the supercomputer, even for sequential, then you can have a lot of small jobs that you do on a whole data set that you can then send to all different cores on the nodes, and then you get a lot faster your computations because you have a lot more cores available compared to your basic laptop. Then for parallel software. So if you're parallel software, you can, if you want to go, if you want to go have like a multi-core job, so you're still on the single node, or a single worker node on the cluster, then you're going to have OpenMP used in the software. If you want to use a bunch of worker nodes within one cluster, you're going to have an MPI software. And so these softwares are built and made and compiled so that they will use all the resources that are available in your job to scale up the performance of the software and get as fast as possible if it's done right. So here are some more pictures. So here is the data center on the top, which we'll visit later today. And then you also have some pictures within the data center. And here on the picture on the bottom with the artwork, that's our current tier 1 for VSC. So at the moment, UGent is also hosting the tier 1 compute here at UGent, but in 2026 or the beginning of 2026, the new tier 1 supercomputer will be hosted at VUB. So then this one will be slowly turned off, but it will probably still be around until 2027, 2028. Okay. So a little bit of the sizes of supercomputers. So I just mentioned that we have a tier 1. So on the basic level, so your own workstation or your laptop, that's like tier 3 compute. Then if you go one tier up, then you have the clusters here at the University of Ghent, so tier 2. And we have four centers in Flanders which have tier 2 systems. So you have Leuven, Ghent, Antwerpen, and Brussels. And then so we also then have the tier 1 computers here on a regional level. And then we have also, if you want to go even higher steps or even greater supercomputers, then you have possibilities on European level via Euro HPC, and you can get information on via EuroCC. And then I'm going to leave it to Kenneth.
Yeah, so this pyramid, not pyramid scheme, but pyramid structure. As you climb up, things become bigger, more expensive, more difficult to work with, and typically fewer researchers using them as well, because they're not so easy to use. But let's start at tier 2. So we're going to ignore tier 3, that's your own laptop. Let's start looking at tier 2. So what do we have here at Ghent University? Currently, we have actually 7 separate clusters. Each of them has a certain age or a typical usage pattern. So we have 3 CPU-only clusters, 3 GPU clusters, and one special case, one interactive debug cluster. I'll explain what all of this means. Getting access to this is available for all academic researchers in Flanders, and the funding is centralized through AWO. So you get access, but there's no bill coming afterwards. Everything is already funded, and you can use the system free of charge. That's for academic researchers. For industry, they can also get access to it. There's a free exploratory period where they can test and play around to get a feeling of how it works. And then after that, there's a contract set up, and they basically pay what they use. So if they run for 1,000 hours of compute, that's also what they pay. The prices there are a lot more interesting to what you get from commercial cloud like Amazon or Azure, for example, because there's no commercial uplift. We just charge you what you're actually using, and that's it. What's important is that all of these systems, all of these tier 2 clusters, are running Red Hat Enterprise Linux. So you have to get yourself familiar at least a little bit with Linux as an operating system. It's not Windows, it's not Mac OS like on an Apple laptop. It is a bit different, and it takes a bit of time to get used to it. But again, we have lots of documentation on this. You can get help if you have any questions, if something isn't working or you're not quite sure. And these days, services like ChatGPT and stuff are actually quite good at least basic usage of Linux. So you can get pretty far with using some AI chat system. Let's take a look at the CPU-only clusters first in a bit more detail. So we have 3 of those. The oldest one, Doduo, currently is still the default cluster. That's going to change relatively soon. So this is 128 worker nodes. Each of those worker nodes have 96 cores, so almost 100 cores compared to your laptop, which has 2, 4, maybe 8 if it's an expensive one. And each of these nodes has 250 gigabytes of memory. So if you add all this together, that's already quite a lot of compute. And that's just one of our clusters and the oldest one, which is now about 6 years old. So each individual node may be a bit slower than your laptop, actually, if it's a recent laptop. And certainly these new Apple laptops, for example, have a way better CPU than what's in here. But you have a lot of CPUs in there. Just we have, let's say, 12,000 cores already in this one cluster. Then we have 2 more. Galate is a high memory cluster. So here you have about 1 terabyte of memory. So not disk to store data, but memory for live data while computations are running. So close to 1 terabyte of memory for 128 cores in each of these nodes. And we only have 16 of those because memory is not cheap. And then Shinx is essentially sort of a replacement for Doduo, although it is a bit smaller. It has about a third of the nodes, but it does have double the amount of cores for each of the nodes and a bit more memory than Doduo has. So you can see these are essentially, when you go from the top of the list to more down, these are newer computers, and things are a little bit different in terms of number of cores, available memory, how fast they are, how big the cluster is as a whole, and so on. All of these systems, all the nodes are connected with a high-speed network. So that means if you're running a calculation like Lara explained with MPI software, for example, where you can use multiple nodes, say 10 nodes and all the cores in those nodes, so that's close to 2,000 cores in total, you can exchange data between each of these cores very fast due to this internal InfiniBand network. And there's a picture here which is not going to tell you much, but these cables, for example, are special purpose cables, quite expensive cables. There's switches connected to this as well. So, and there's tens of gigabytes per second of data transfer possible between these 2 nodes. So it's very, very fast. From each of these nodes, you also have access to the shared file systems. I'll explain more what that means. And each of them also has a local disk, just like your laptop has, which is quite fast, and which has maybe a couple of hundreds of gigabytes of data as well. So you can store data there while your job is running, store results there, and you should copy them back to the shared file system before the end of your job, or you will lose the data. So every time something is, a job finishes, let's say, all the data that it has stored on local disk is automatically removed. So we clean stuff up again for the next workload that will start. But I'll get back to that as well. So 3 CPU clusters. We also have 3 GPU clusters. These are smaller in terms of number of nodes because they have these fancy GPU cards in them. These used to be for gamers, for video games. But since quite a while now already, these can also be used for scientific computing. So to speed up certain types of scientific computing. And of course, with AI, you've heard probably already about GPUs. And they are a very good fit for training AI workloads or running a chat, an AI chat system, and making sure that it can give you fast responses. So we've been using GPUs for quite a while already. Also, Joltik is now close to end of life. But each of the Joltik nodes has 4 of these GPUs in them. Each of them have their own amount of memory as well, 32 gigabytes. And again, as you go down the list, it's newer hardware, more capable hardware. So you can see the number of GPUs per node stays the same, but the memory grows quite a lot. And that opens new doors for new types of scientific workloads running on them. And they're also a lot faster. They're also quite more expensive. So that's why the number of nodes is actually going down in these clusters. I used to say a single GPU is about a car, maybe not a very fancy car, these old cards. These are now a really high-end car. So each GPU is about the cost of a car. So you can imagine how much money the whole cluster costs. Also same here, fast network between these nodes, so you can exchange data quite fast between different GPUs, access to the shared file systems, and again, a local disk as well in each of these nodes, which you can also use. Is anyone seeing a pattern, by the way, in the names of these systems? Yeah, they're all Pokemon, right? That's why the funny pictures are there. So we give a name to the clusters just because it makes it easier to say where your workload was running, what you were using, and also for us, if we need to point to a particular system, we each give them a name, like you do with children, I guess. One more Pokemon, the special case, the interactive debug cluster. So this is something we started doing a couple of years ago. This is actually quite old hardware, so it's recycled hardware from a system that was retired already over 2 years ago. So the hardware itself is quite old and worn out. But in this case, that doesn't matter too much because what we want to do here is give you a cluster where you can start a workload instantly without waiting in the queue until enough resources are available. This also has a small GPU, so you can actually do some GPU workloads on this, but the GPU is shared. So that means if other people are running jobs on the same node as you are, you may be fighting for the GPU, essentially. So you each get a turn every now and then, and that slows things down quite a bit. So this is not going to be a fast cluster. It's old hardware. It's shared. We also oversubscribe the hardware, so that means we're running more jobs than there are cores available. So if there's, let's say, 1,000 cores available in this cluster, and there's enough jobs to run on 2,000 cores, we'll just keep starting jobs. So things will get slower and slower. In practice, we don't actually see that this system fill up quite heavily. So the oversubscription is in practice rather limited. There are limits though. So we need to keep things under control. We cannot allow a single person to submit thousands of jobs on this because then it's going to be slow for everybody. So there's a limit of a maximum of 3 jobs that are actually running and 5 jobs that you can submit that are in the queue, either running or waiting to be run. And there's a maximum of 8 cores that you can use in total for running jobs and about 27 gigabytes of memory. So that essentially says that you're getting the equivalent of, let's say, a laptop on the cluster in the exact same environment as all the other clusters are running. So you can test your software, test your job scripts, test how things work, and you don't have to wait in the queue until it's your turn. So we've learned that this is a really good way. People like this a lot because they can play around if they don't need a lot of work, a lot of resources, and they don't have to wait in the queue. And especially for interactive use, Jupyter notebooks, graphical user applications, a desktop environment, things like MATLAB, VTK, this type of software is very easy to use on this system. So there's no waiting time, but there's a downside to that as well in terms of limits and in terms of how fast this system is. There's a whole chapter on this on the documentation as well. I will actually show this quite a bit today. All right, so this was tier 2 in Ghent, but with your VSC account that you all have by now, you can actually also access the HPC clusters in Antwerp, Leuven, and Brussels. You can log in there straight away. That should work. You'll find the same home directory there. So the files you have in Ghent are also in Leuven and Brussels and Antwerp over a not so slow connection, but it's not fantastic either. So there is a bit of a hiccup there in terms of latency of accessing that data, but it does work. So in theory, at least, you can go to other clusters if you don't like the ones in Ghent and just run your computations there. That will work. The system is largely the same. It's also Linux. It's also similar hardware, GPUs, CPUs, different generations. But the way things work there are typically a little bit different. So you do have to check the local documentation of these systems to understand how it's different from in Ghent. And on 2 of the hubs in Antwerp and Leuven, there's a credit system as well. So there, you need to essentially pay for what you use, but I think it's 5 or 10% of actual cost. So there is a bit of an extra hurdle here on at least 2 of the hubs. That's not the case in Brussels or in Ghent. So there you can just log in and compute, and everything is paid for already through FWO. So that's useful to keep in mind. Check the VS Centrum, so the VSC website, the documentation part with an overview of the hardware. You can take a look there if there's a particular GPU that you know works better for your workload, for your software. You can go there and at least consider running your computations there. Then going up the pyramid, looking at tier 1 level. So a bigger system, more expensive system, more capable system. So this is currently running in Ghent still. We've been running the system since 2021 for the Flemish Supercomputer Center. This has 2 big GPU partitions, each with about 380 nodes. So you can see there's already a step up in terms of size compared to tier 2. Each of the nodes has 128 cores, 2 different generations. And in total, we have 40 GPU nodes, each with 4 A100 NVIDIA GPUs, so 160 GPUs in total in this system. If you count all the cores, we have just over 100,000 cores in total in this single system, if you count everything together. Again, very fast network, dedicated scratch storage, so a shared file system across all the nodes that's 6 petabytes in size, so 6,000 terabytes, 6 million gigabytes. That's quite a lot. And there are some people who are using this really well, so hundreds of terabytes of data being used on this for a particular project. The way of accessing the system is a little bit different. It is with your VSC account. You can also access the same data, or at least part of the same data that you have on the tier 2 clusters. But to actually be able to access this and to run computations there, you need an active project. So you need to do some kind of project proposal, explain what you're going to do, explain how you're going to organize the workloads, which software that you're going to use, what you're going to do with input and output data, how that's all organized. So you need to show that you're prepared to use this system. And when your proposal is accepted, then you get access for about 6 to 8 months to run your computations. So there's an extra hurdle there because we want to make sure that the system is used well and only for big things that are not a good fit for tier 2. Once you do get a project, there's no charge, at least for academics. And we're now pushing industry people more and more to these big systems because there's more breathing room there, let's say, to let them do their job as well. And they do pay for what they use. So as an order of magnitude, you need at least 500,000 core hours. So a core hour is running a computation for 1 hour on a single core. For your whole project, that needs to be at least 500,000, or we say this is too small for tier 1. So there is a bit of a limit there. And similar for GPU, you need at least 1,000 GPU hours in your request, or we consider it too small. Again, more information on the VSC website and in the VSC documentation that has a lot more detail on this system. It's really, since we're running this in Ghent, and we have a lot of tier 2 clusters in Ghent as well, to us, it's more or less a big tier 2 system. So we operate it largely in the same way, but it is different hardware, it is a different vendor, it has its own quirks and problems. But to the outside world, it's mostly another UGent system, let's say. So this has been there since 2021, 2 partitions. It has a lifetime in total across the partitions of about 6 years. So that means by the end of 27, probably, we're going to turn this off. Its hardware is too old, it's becoming too cumbersome to maintain it. But we already have a replacement plan in the VSC, in the VSC. So very soon, even this could be even still this year. They hope they'll be able to put the system operational this year in Zellik, so operated by the Vrije Universiteit Brussels, the VUB. This is an investment by the Flemish government of 8.6 million euros for buying the system, keeping it powered on, having people to support it and operate it and maintain it. This is going to feel smaller than the previous tier 1, but that's because the prices of hardware have gone up crazy the last couple of years. So we're getting more or less the same budget, actually I think a little bit more than for the Hortense system, but we're just getting less in some sense for the same amount of money. So it's fewer cores, about a quarter of the cores we have in Hortense, although some of them have quite a bit of memory available, and about 160, so roughly the same number of GPUs we have in Hortense, but they're the latest generation of Hopper NVIDIA GPUs, and they're insanely powerful. Again, very fast network, some visualization nodes to do visual work, visualization of scientific data, and lots of scratch storage, again, 4.4 petabytes of storage, and then some very fast NVMe, so SSD type file system as well. To give an idea of power, this thing consumes about 350 kilowatts, so that's rather a lot. I don't know the numbers of how much it's going to cost for power, but I know for Hortense, keeping Hortense powered on for a year is about €1 million just for the power. Double?
The peak consumption.
Yeah, so peak consumption of Hortense is about 600 kilowatts. So, I mean, of course, newer hardware is more energy efficient, although these GPUs definitely don't help there. But it does give you an idea of size. So that's tier one, current tier one in Ghent, next tier one coming very soon in Brussels. So there's, let's say, guaranteed resources available, at least in Flanders. This was tier one compute. We have a tier one cloud as well to maybe make it more confusing. This is a bit similar to, let's say, Azure or Amazon, where you can get some resources for virtual machines. So you essentially get access to hardware, and then you're on your own. You install the operating system yourself. You can run Windows on this if you want to, but you have to manage it yourself. So you need a bit of experience as a system administrator, how to keep this running. Similar here, project-based access. Once your project is approved, no charge, at least for academics. You get virtual machines, some of them with a small GPU in them, but you manage them yourself. So there are use cases here that are not a good fit for the compute cluster, say running some kind of web portal where people can submit workloads. That's typically something that runs on this cloud environment. Again, I won't go into too much detail here, but this is well covered in the VSC documentation, and there's a separate support email address here if you have any questions related to this. All right, Lara.
Who can get access, who can get a VSC account and who can get access to our infrastructure? So all members of UGent association can request an account. So that is researchers and staff, but also master and bachelor students. The VSC can, oh, Kenneth, something happened. The VSC infrastructure can be used. Okay, so that one. Okay. So VSC account can be used to access the HPC infrastructure on all VSC sites. You will automatically be subscribed to two mailing lists, so the HPC announce and the HPC users. You can unsubscribe from the HPC announce, right? Or the other? Yeah. From the HPC users if you want to, but as long as you have an active account, you will be subscribed to the HPC announce. You can also use it for teaching services and exams, but be aware, especially we just had like an emergency shutdown of the system, so we can never guarantee that the HPC will be available. So if you organize these teaching and exams, always make sure that you have a backup plan. And so, yeah. So, and we also advise that if you do teaching and exams on it, that you use project work so that the students have like a period of time where they can do it, so that if the system goes down in that period, that it's not the end of the world and that they can still do their work. There's also information, and if you want more information on getting a VSC account, you can find it in our documentation. How do you manage your VSC account? You do that via account.vscenter.be. You can request more quota if you don't have enough storage anymore in your account. You can request a new virtual organization or joining an existing one, and all that kind of stuff you can find in this portal. So yeah, I'm now going to go through like what a workflow on the HPC infrastructure can look like. So the first step is to connect to the system. So how can you get access? There are two ways that you can get access to the system here at UGent. You can either do it old school via terminal with SSH keys, or you can use our web portal, our web portal. So it's much easier to do it via the web portal. You don't need to know about SSH keys. If you're on a Windows computer, you don't have to figure out how PuTTY works. So in general, we recommend that you use our portal to access the system. And so once you're on the system, you'll be on one of our two login nodes. That's Glider 09 or Glider 10. And from there, you can manage your files in the file systems, but you can also then submit jobs to the different clusters that we have on our system. And so the worker nodes are also connected to the file system so they can be used in the jobs. So this is general explanation of how to log in via SSH. So you can do it via the web portal by clicking on clusters. So if you're not doing it via the web portal, you will need an SSH client and private key. And yeah, there's some more explanation on this, but this is also documented. So the second option is what we will recommend is via the web portal. It's just going through the site login.hpc.ugent, and it should work on any standard browser, so Firefox, Chrome. And you do not need to mess with the SSH pair keys. Okay. And so you can do everything from there. You can have shell sessions, you can have desktop environments, you can have interactive apps like Jupyter Notebook and stuff all on there. And so here is how to manage your files on the file system via the web portal. So you can create new files, you can delete files, you can go through the different storages that we have on the system. Kenneth will go later through what the different storages are there and what's the difference between them.
As a quick demo, the portal.
Yeah, you can. Then also to create an interactive app, like for instance, Jupyter Notebook, you can click here on interactive apps on the top, then choose Jupyter Notebook, and then you can go into on which cluster you want to. So here's Donphan is specified, how long you want to have that session running, how many nodes you want, how many cores you want. On the GPU clusters, you can also then specify if you want to have GPUs. And you should specify the version of the Jupyter Notebook. So if you want to run more software than the standard Python. So for instance, if you want Peeters in there, you have to make sure that the PyTorch module that you specify in the the PyTorch version is the same as the Jupyter Notebook version, so that they are compatible. Otherwise, you can have trouble. And so once you click on launch, the job will be queued. And if it's on Donphan, it will start very quickly. And then once it's running, you can connect to it. And then you can land on the standard Jupyter Notebook interface if you're used to using it on your laptop. So what you can also have as an interactive app is a desktop, just the same as with the Jupyter Notebook. You can specify the cluster, the hours, the resources that you want, and then you have a Linux desktop. So if you're used to using Linux, it will be very familiar to you. If you're new to Linux, it might be a little bit of a learning curve, but it's not that big of a difference than a Windows or a Mac OS in desktop. And from a desktop, you can then run programs that require a GUI. So if you've already once tried to get access to the system outside of the UGent network, you might have landed on a page that said you hit a firewall, like you have like you need to connect to the firewall app. So it's very easy to use. You click just on the link. It will ask you to log in via the the authorization. And once you're authorized, you will land on the firewall app desktop browser page. And as long as you want to keep connected to the supercomputer, you have to make sure that this browser stays open, because if you close it, you will be locked out again. Okay. Then you can also have shell access to our login notice by clicking on cluster, and then you will land either on our Glider 09 or Glider 08. And if you're used to using the command line, you can also manage the file system, submit jobs via the login notes. So some basics of Linux that might be very useful if you're going to start using the supercomputer. So are, for example, commands like ls, cd, mkdir, which are commands to manage your file system. Yeah. We also have documentation on this under Linux tutorial in our documentation. So yeah, to learn all the different commands that are out there. Yeah, we strongly recommend that you at least learn the basics of Linux shell because yeah, Linux, knowing how it works can be very powerful. And yeah, so.
Yeah. Okay. Before we move on, we're about halfway. Let me do a quick demo of the web portal. So when you go to login.hpc.ugent.be, I won't log out here, but it's going to make you log in. So if your VSE account is connected to your UGent email, you select Ghent University. You'll have to enter your UGent password, and then you should land on a page like this. This is the starting page. Here it gives an overview of how busy the clusters are. You can see Joltik, for example, has one node with 4 GPUs that is fully taken, 0 nodes that are totally free, and 9 nodes which are partially free. So that probably means that one GPU or multiple GPUs are available in this. And you can see the same thing for all the other clusters that we have. Now this is a snapshot. It updates, I think, every minute. But it does give you some information of how busy things are. Usually the free nodes column is all zeros. That's good for us. That means our clusters are being well used. But every now and then, and especially on Donphan, you can see there's a lot of room to run jobs. And on Donphan, they are quite small, of course. So Lara showed the file browser here. Here, if you click this, you can see all the different locations that you can put data in. So it's not one hard drive like you have on your laptop. But it's different directories, and where you put stuff matters. I'll explain a bit more in the upcoming slides when it matters and what you should put where. But there's essentially a home, a data, and a scratch file system. They have different intentions, different characteristics. And in each of these locations, they may have additional subdirectories as well. If you're a member of a group of people using the system, a virtual organization, which typically corresponds to a research group, you have additional directories in that VO space as well. So that's why you see all these entries in here. You can click one of these. You'll get an overview of all the files in here. This is taking a bit of time because I've had my account since 2008. And I haven't cleaned up in a while. I have like 12,000 files in my home directory, which is a bad idea because that makes things slow. That's what you're seeing here. It will come back eventually with a list of what's in here, so I'll let it think a bit. Very bad practice. That's why I'm showing it, but so everybody knows they shouldn't do this. But also here you can click again to each of the other locations. I hope it's actually going to fall through because I don't want to show what this does. Now, while we wait, yes, there it goes. You can create new files here. You can create new directories. You can upload files from your laptop into your VSE account. All the way around, you can download files or directories from your VSE account to your laptop. You can also access Globus here. So Globus is like an easy way of moving big amounts of data between systems. More on that in the documentation. But here, this is very intuitive. So this is just directories. And let's find an interesting one. Cellpose is a scientific workload. This only has one file, so this is a bit quicker. This is an image. And if I click this, I can actually see the image. I go back and click this here. I can do edit. Now, this is an image, so this is not going to work well. This is an editor for text files, of course, so this looks funny. There's not much useful here. But you can imagine if there's a text file here, I can actually create one. Example.txt. The extension doesn't really matter. Linux doesn't really care typically. But if I edit something here and say hello, and there's a save button somewhere. Oh yeah, okay, it's not popping up. Well, this is a save button. I hit save, just close this. And then when I go back to here and do view, you should see the hello there. And these are the exact same files that you can also see in your Linux shell environment. So if I start a Linux shell here, like Lara also showed, and if I go to the cellpose directory in here, so I'm doing cd into cellpose, ls to check what is there, I can see the same files and I can check the contents of the files that only have hello in there. So these things are instantly synced. You don't need to worry about delays or something. Whenever you change something in the web portal, you'll see it in the shell and the other way around. All right, and then interactive applications, this is where it gets interesting. You can start, for example, a Jupyter Notebook environment. Donphan is a very good cluster to select here because that will allow us to start the session instantly. But we do have a limit here of how many cores we have available, how much memory we have available. It's typically not a good idea to only ask for 1 because that will make things quite slow, but 2, 4, or let's say the full 8 that you can get makes sense. You can pick the Jupyter Notebook version here. You need to be a little bit careful with this if you not only select Jupyter Notebook, but also load additional software in here, and I'll get back to that with the module system. You need to make sure that these are compatible, but for now, we'll just launch a Jupyter Notebook. You'll see this goes to queued, and this will auto-refresh. So as soon as the job is started, this will show a button that we can connect to. While it's doing that, I also want to highlight this. So this is a session ID that you can click, and this drops you into a directory that has lots of files in here. These are all the scripts that are used to start a session. Most of these are not interesting to you, but what is interesting is the output.log. If your session fails to start, so it like starts and immediately stops again, this is the file you want to look into to see what went wrong. And again, here you'll see lots of details. And typically, if there's any problems, they'll be towards the end. This one is actually not the real problem, I think. But if it fails to start, you can definitely check the output.log file that you can find behind the session ID. Or if you're not sure, you can click Submit Support Ticket and answer or fill in the boxes here, give a description of the problem, and we actually get all the session data along with your request. So we get a lot of background information straight from the system. Now, I started an interactive app. This is hidden behind this button here. I can connect to it. This will again open a new tab in the browser, and this should show a Jupyter Notebook that you can start playing with. I asked for 4 cores. I didn't ask for more time, so I kept the default, which means I have 1 hour to play around in this notebook. After 1 hour, the notebook is gone. So that's something to keep in mind as well. You can ask for up to 72 hours in a session. And just keep an eye on that as well. Yeah, and here the notebook is running, so I can start if it wants to. It's a bit slow today. Not sure why. Okay. Yeah, it has dropped. See, this is why it's a bad idea to have many files in your home directory. But I can start a new notebook here. This will again open a new tab. And this is when you can start playing with running Python stuff in here and executing that. And doing visualizations, data analysis, all of this interactively in a session that is actually running on one of the worker nodes of the Donphan cluster here, node 4060.
You can also specify a bit of paths. If you don't want to start from the home directory, you can also start paths.
Yeah, there's more options here that I didn't cover. You can specify where you want to start. So if you know where your notebook is located, you can specify directory here. You can add custom code that will run before Jupyter actually starts, extra arguments for the Jupyter command when your notebook is started, and so on. There's a hidden button here or hidden section, advanced stuff. You can increase the timeout if you see problems with the notebook being started, and so on. So you can explore that a bit. And we have similar interactive apps for RStudio Server, for VS Code, also for desktop environment. That's an interesting one to show as well. So I'm only using 4 cores in the Jupyter session, so I have 4 cores left to start another session on Donphan. This is a desktop environment, like Lara also mentioned. This is very close to a laptop, let's say, but it's going to be a Linux desktop, so it maybe look a bit scary at first, but I can connect to this here as well, and say start a terminal here to activate MATLAB. So I load a MATLAB version. I'll get back to the module system in a bit, but this is how you activate software to use. So this is MATLAB 2023A, and if I now start the MATLAB command, it will actually start the MATLAB session. So it's now starting. Now let me show you if you're on a train and you lose all of this, connection is broken, this goes away, everything is dead. You log in again to the web portal, you can actually go back to these interactive apps and they're still running. So I can connect back to this desktop and the MATLAB session is now still starting, but you can see you can play around a bit. If your session runs for long enough, you can start stuff today, come back tomorrow. That's fine, at least when you're using the interactive debug cluster, that's okay to do. Yeah, so you can see this really lowers the bar to entry. It's very intuitive to start interactive sessions, to get shell access. There's no SSH key shenanigans going on. You can access all your files. There's a job overview here as well. I don't recommend generally using this, mostly because we don't have too many experience with this, but you can actually see which jobs are active here across different clusters even. And there is Job Composer as well to create jobs. But in general, we recommend creating job scripts in your account and then submitting them through the command line instead. Although this may actually work. We don't get questions on this, so I suppose some people discover it and try it and it works fine. But in general, we don't recommend this. All right, so that's an overview, an interactive overview of the web portal. Let's get back to the slides. But since we're now about halfway, maybe now is a good time to check if anyone has any questions already. Yes?
We started the session, so sometimes we choose specific hours, like 1 to 2 hours. So can we adjust the session before the end of the session itself? Like we go back and just like increase the hours or increase the
No. No.
Can't do that.
No. So no, that would be cheating, right? And there's a reason. There's a reason for this. So the question is, once your session is running, can you make it longer than what you originally asked for? Yeah. Yeah. No, you can't. This will actually become clear in one of the upcoming slides, because that would be a trick to get access to more resources. If you're asking for a shorter job, it will be easier to get it started. On Donfan, this is not relevant, but on the other clusters, if you start for 1 hour, let's say, ask for 1 hour, the system will find a gap of 1 hour and say, okay, you can go. If it's only 1 hour, I don't really care. If you ask for 3 days, it needs to make sure you have 3 days of time, and it needs to find a gap that's big. If we would allow your session to expand while it's running, you could say, I'll just ask for the session for 1 minute, and the first time I'll extend it to 72 hours. So that's the reason why
No,
you can't.
I mean, like in case like you are about to finish your job, just like 30 minutes extra. So
yeah, no, not even a single second. No. So you need to think ahead.
yeah,
yeah, and so the 3 days is a limit. From my part, you can always ask for 3 days, and it's fine if you don't use that time. Eh? If your session ends earlier, no problem. The remaining time will be for somebody else to use. That's okay. So you just need to think ahead and try to estimate.
If I take more time to back the other as well.
Yeah, if your session ends, that time is released for somebody else. So that's not a problem. Yeah. Yeah, that's coming up in one of the slides.
How much time you try to get close to that time. So let's say if you expect 10 hours, you must 12, 13. Then you will be fine, but then it helps everybody. It helps the system to work more.
Yep. This is one of the typical first questions that we get. How do you know how much time to ask for? It's practice, trial and error. Depends on the software, depends on the cluster that you're using. Yeah, there's no good answer. Yes. Yes.
And you want to not make it too high,
Mhm.
so that you would probably need it to run longer?
Yeah. So the first question is, what if you need more than 72 hours of wall time? Then you need to break up the problem into smaller parts, essentially. Either you can do that by, depends on the software that you're using as well, but maybe you can do that yourself. Just say, I'll do the first part in one job, get the results, and then I'll create a second job that uses those results to continue the computation. Some software supports that. So this is called checkpointing, where you essentially dump intermediate results and then restart again later. Sometimes it also helps to ask for more resources. If your software scales well, you could ask for not 4 cores, but maybe 100 cores, and maybe it becomes significantly faster to squeeze it within the 3-day wall time limit. Sometimes just also using a newer cluster can help. So like I said, here, for example, Duo is the default cluster, but this is hardware that is 6 years old. So it's like using a 6-year-old laptop, it's going to be slow. If you go to one of the other clusters, like Shinx, this is significantly faster. Shinx is by now, I think, about 2 years old. So you're using newer hardware, which is probably going to run your jobs faster as well. So just by being a bit smarter where your job is being sent to, you could also fit into the 3-day wall time limit. I'm running ahead a bit. This is coming up in one of the slides, but the reason we have a 3-day limit is so we can do maintenance on the system when we need to. And this actually happened just last week. A security issue was announced on Friday, and we said we're going to shut down the system. Nobody accesses it anymore. And we used the weekend to update the system. And on Monday, at least for tier 2, it was back on Monday. The only reason we can do that is because we have the 3-day limit. So there is advantages to this as well. Yeah. It really depends on the software, and that's maybe a good question for the hands-on this afternoon. 3 days is a hard limit. We don't go beyond that. And on some systems, like in the Netherlands, for example, in Surf, I think they have a 1-day limit. 24 hours, that's all you get. You just have to learn to deal with this. Yeah. Yeah.
It takes much longer.
There are ways to speed that up, to use more cores or to chop it into smaller parts. And yeah, there's techniques to do this.
And if there's really no option, then you can move to the cloud, but then you have to do all the setup of the software yourself. Then you can extend the wall time as long as you want, but then you have to set everything up yourself.
Yeah.
So
this one use case for this is, let's say, a workload that needs to run for a month, to do a month of computation, and it cannot be made faster, it cannot be parallelized to use more cores. That's one of the use cases for cloud as well. But there's a hurdle here. You need to propose, you need to explain why you need these type of resources, and you'll need to manage the virtual machines yourself. So it's like running your laptop and doing updates and installing software. You'll have to take care of that all yourself. Yeah. So this could be part of the answer as well. Yeah. There was, yes. The trial and error.
and it's also in our documentation. It's also in our documentation. So you can check. So if you want a lot of memory, you can check our documentation for the cluster that has the most memory.
It depends. So let's say the first time you run something, try it on the default cluster, see how fast it is. If it works, that's already good. If you're worried about how long it takes, you could try one of the newer clusters, see how fast it becomes. Maybe it's a lot faster, maybe not. So that will determine where you go. And just also how busy things are could also help. So if you log in to the web portal, you see how busy things are here. And let's say Shinx looks really busy now, 45 nodes totally full, 3 nodes partially full. That doesn't look like a lot of breathing room to get a job started soon. Dodo looks a bit better. Is this Donphan? Yeah, Donphan now has 14 totally free nodes. So if you only need 8 cores, that would be a very good fit. That can also help you, that you don't need to wait too long in the queue. But it's a very difficult question to answer. Depends on the software, depends on your workloads. Are they getting faster with newer hardware? Do they need a lot of memory? Then maybe you're stuck to Galade, which has a large amount of memory. It really depends on what you're doing, and it depends on maybe when you're submitting even. Yeah. Yeah. So yeah, I mean, maybe yeah, maybe you need more memory, or also the memory is faster itself as well. So if your software is using memory all the time, it could be beneficial from using one of the newer systems as well. Yeah. Yeah, so there's lots of factors there. Maybe you need GPUs, or your software can use GPUs, then these are interesting. But maybe these are always full all the time, and then you want to do something else. It really depends on what your software is doing. Yeah. There's another question there? Yes.
You submit,
Yeah.
and then you submit it again, but you change the script
Yeah.
between.
When you submit the script is copied. Yeah. So yeah, I was about to get to that. I was maybe going to show it in the demo. But when you run the qsub command to submit your job script is copied to the system, and then you can remove the job script or change it. It doesn't matter. For that submitted job, everything is fixed in time. Yeah. Yeah. It doesn't affect the jobs in the queue.
In general, I think it's not very
Yeah.
good, but
Yeah. Just copy the script, rename it. Yeah.
Sorry.
Yes.
I tried to open the cluster into Visual Studio.
Yeah.
Opened in the web,
The web portal?
browser-based, yeah.
Yeah.
And I couldn't open it in the application.
Okay, that's something for the hands-on to look into. So you want to connect from VS Code into the...
I can, but it just opened in the browser.
Okay, that's something for this afternoon, I think, to look into together. Yeah. Any other questions before we continue? Oh, pretty good question so far. Running ahead a little bit, so I'll actually partially answer some of these, but okay. So we've showed you what is there in terms of resources. We showed you the web portal, so you can check where your files are, run interactive apps. But at least historically, HPC clusters are mostly intended for what's called batch jobs. So a job script that you describe what type of computation needs to happen. You submit this to the system, and then you wait. You wait until the job starts. You wait until the workload completes. And this could be days, hours or days until it runs.
say hours and days, so now the academic year starts. That's good fun.
So things can be quite busy. Yeah.
And it's really easy.
So how does the job submission system work? In Ghent, today at least, it's still a bit of a complex story. We're running Slurm as the resource manager. So this is what most supercomputers run to manage the workloads. But we still have a different front end. So the front end is still the old PBS front end. So this is the qsub, qstat commands that you'll also see in the documentation. Qsub to submit a job, qstat to check which jobs are running or are queued, qalter to change jobs but before they start running. So you can submit the job with 1 hour, qalter to 72 hours, but only when it hasn't started yet. Qhold to put holds on stuff and release them again later. And qdel is actually missing here, but that's coming up. So all of these commands were used on the cluster essentially since they were there. We still have them, but in the backend, things have actually changed. And we may actually start working away from this relatively soon. For now, this is when you're doing batch jobs and job scripts. These are the type of commands you should use. If you want to figure out what's going on in the background, when you run a qsub command, you can use the --debug option, and it will unpack, let's say, what's going on in terms of translating things to Slurm and running the actual job submission. You can also do a dry run to check what would happen without it actually happening. And the --help will show you all the options that each of these commands have. So to use these commands, you need job scripts. So what is a job script? A job script is really a text file. It's like a small program, which maybe sounds scary, but it's actually not that scary, and I'll unpack it step by step in the coming slides. The text file specifies shell commands, so stuff that should be run on the Linux system where your job will be executed. There's actually 3 big parts to a job script. There's the resources that you're requesting, how many cores, how many nodes, how much time, how much memory, maybe GPU or multiple GPUs should be specified typically on top of the job script. You'll need to specify which software you want to use for the calculation. That's typically done through module load commands, which I'll explain. And then the rest of the job script is the actual work, the actual shell commands that will prepare some input files, run a particular software package with maybe some options and parameters, and then at the end doing something with the results of that computation. So step by step, let's look at the resources first. So typically a job script starts like this. The first line is usually hash bang bin bash. This just tells the system it's a bash script. Bash is a type of Linux shell environment. If you're not sure, just always include the script and it won't hurt. The next couple of lines, these hash PBS lines, specify resources or meta resources like the name of the job. You can pick a name, and that typically helps you to figure out what the job was doing, or especially when you're submitting multiple jobs, maybe even hundreds of jobs, you want to give them good names so you can tell what is what. The second line here, the PBS minus L, so not -1, but minus L, small l, says nodes equals 1, ppn equals 4. This essentially means we're asking for 1 node and 4 cores. The ppn stands for processors per node. It should actually be cores per node. This is historically, computers only had 1 core a long time ago. That's why it's still like this. But you're actually asking for 4 cores. In this case, we're asking for 10 hours of wall time. So we're asking the system, please give the job script 10 hours to finish. If it takes longer than 10 hours and 1 second, the job script is stopped, no questions asked. If it finishes after 1.5 hours, that's fine. Job script completes, generates all the results, and the remainder of the time is made available to other jobs. And sometimes it can be interesting to ask for more memory, in this case 50 gigabytes of memory. By default, you'll get a certain amount of memory connected to the number of cores that you ask for. So if on average there's 1 gigabyte per core, if you ask for 4 cores, you'll get 4 gigabytes of memory. That may not be enough, and then you can increase the memory request by using the vmem resource line. And then the rest of the job script comes as well. All these hash things are comments in the job script. So you can put text there, documentation for yourself to help you out what's going on. The system will just ignore these lines essentially, except the ones that start with hash PBS. As already mentioned, there's a limit of 3 days, 72 hours that your job can ask time for. If you try more, the system will just refuse the job, or it will never start. I think it will actually refuse the job from being submitted. Yeah, and if you have longer calculations, you somehow have to break it up into shorter jobs, use maybe a different cluster, a faster cluster. Maybe there's software around there that can use GPUs and like squeeze down the time from 10 hours to maybe 1 hour, if you're lucky. Maybe you can use more cores if your software scales. So like Lara mentioned, if your software is using OpenMP for threading or MPI for multi-core, multi-nodes, you can try using 2, 4, 8 cores and just see what happens. If the software becomes faster, that can help as well. Or if needed, some kind of checkpointing where you store all intermediate data and then later reload and continue the calculation. So there's lots of options to explore. Then the software part of the job script, we have a big central software stack via the module system. So very quickly to give you a feeling, let me open a shell here. Make it a little bit bigger. And run a module avail command. So this will show the software that we have available in the central software stack. This is a long list of software, right? So this is literally thousands of software packages that are available. These at the end here are actually extensions. Oh boy. Let's do it like this. So this will show the software actually on top. So all of these things, different versions of Abacus, different versions of Amber tools. You can see I'm scrolling down, but I'm still at C. So there's literally thousands of software packages pre-installed. The module avail will show you everything. That's probably going to be too much. but I can do, say, module avail MATLAB to filter it down a bit. And this will only show the MATLAB versions that we have. You can start searching if the software that you're interested in is already there or not. If it is, it boils down to just loading that software either interactively in a shell session or in your job script to activate that software for being used. So essentially, you'll have typically multiple module load statements in your job script that activate some software and make it ready to use in the job script. All the module names have a certain structure, so it always name of the software, version of the software, then typically the tool chain, the compiler that was used, or the version of the compiler that was used to install that software that may be relevant because you can only load things that are installed with the same tool chain. So if you're loading multiple packages, they have to be compatible with each other. Yeah, so here SciPy bundle is a name we invented. It's a bundle of different Python packages for scientific computing, a certain version of that. So this was installed in July 2023. And this part is the tool chain that was used to install that software. If you have multiple modules loaded, especially interactively, this is interesting. You can run module list to see what is loaded. You can also do this in your job script to get a full overview. With module avail, you can check which software is available. If you give it something after the avail, it will filter down the overview with what matches. And if you have loaded a bunch of modules and you change your mind, you can run module purge to unload everything and do a reset, essentially. And like I already said, the toolchain is important for things to be compatible. If you ignore this, you'll get error messages that say you cannot load these two things together. Right. There's also a dedicated section on this in the documentation, but maybe an example is good. So if you log into the system and you check which Python version you have, you'll find something, the default system Python, which has to be there. We cannot avoid this, which is these days not ancient anymore. It used to be a lot worse, but you'll get the Python 3.9 version, which is not at least very recent. But if you start importing stuff like NumPy, for example, you'll get errors because NumPy is not installed system-wide. To get access to NumPy or many other Python packages, you'll have to load a module. So you do a module load of, for example, the SciPy bundle. You will get no output when this is run. But in the background, this will change things in your shell environment. And if you now check which Python version you have and where that Python is installed, you'll see it has changed to a different location in our apps Gent central software stack, and typically a lot newer version of Python. And in this case, since it's SciPy bundle, which includes NumPy, you can also import NumPy and use it as well. So this is a very easy way to get access to more software that's already pre-installed on the system. So that was the software part. Then the actual work that needs to happen in the job script, you also need to describe. For this, there's a couple of environment variables that are relevant. The most relevant one is the job ID. So whenever you submit a job to the system, you'll get a unique number. That will help you to, well, it mostly helps us actually to trace jobs down the system and figure out where it was running. Maybe if something was wrong with it, we can go and check our logs. But it can also help you. You can use this, for example, to create unique result files from each job. So you can have one job script that you submit multiple times. Every time it runs, it gets another job ID. And if you store those results, you can get unique files, unique output files for each of the jobs. The other interesting one is PBS/workdir. This is the location where your job was submitted from. So you first do CD, you change to a certain directory where your job script is. Typically, you do a qsub of that job script, and this variable will have that location stored. So in your job script, you can do CD to this, and then you know where you are, and you typically find stuff that is relevant to that particular job. I'll have a concrete example of that in an upcoming slide. The other ones are there, but maybe less interesting. Well, actually, the temp there is interesting. This is also this is a directory on the hard drive, on the disk of the node where your job is running. So this is a temporary location. You can use this while your job is running, but as soon as your job stops, this is cleaned up. You can use this to generate stuff, copy back the stuff that you're interested in, And as soon as your job script completes, everything is automatically removed. This is interesting because it is typically very fast, and at least for single node jobs, this can be very useful. Another open question is where does your data come from? The input data that you need for your scientific calculation. Where do you put your results, the output files? These are also open questions. So for this, we have multiple locations, 3 different types of file systems, home, data, and Scratch. And for Scratch, we actually have the fast SSD powered Scratch as well, which is a lot slower, but is significantly faster than Scratch. So 3 different types. The home file system is the entry point to the system. There you have a limit of 3 gigabytes in your home directory, and I think it's 1 million files maximum. That's it. We don't increase this limit for anyone, so it stays exactly the same. But this is typically good enough as an entry point. You can put small files there, maybe job scripts there, and that's absolutely fine. But you typically don't put any big input files there. The data file system is for long-term storage, so you can put stuff there and assume it's going to stay there for as long as we exist, essentially. So I definitely have files there that have been put there in 2009, and they're still there. So we have long-term storage. We used to have backup of this, not anymore, but we do have some data protection mechanisms there. We actually have 2 copies of each file. So if something disastrous happens in terms of hardware, we will not easily lose it, at least. This is also tailored to large files. I mean, large, I mean tens of gigabytes, hundreds of gigabytes is absolutely fine. In this file system, it's well prepared for that. And then the Scratch file system, this is typically for live data. So when a job is running, it has lots of input data, it's generating lots of results. That's what the Scratch file system is intended for. It's significantly faster than the data file system, but we have less protection there in case of hardware errors to lose your data. Up until now, I don't think we've ever lost any data on the Scratch file system, but it's more likely that it will happen on Scratch than it will on data. It is a lot faster, so it does make sense to put your data there when your job is actually running. And then disk space, so how much space do you get? Like I already mentioned, home directory gets 3 gigabytes max. And your Scratch and data directories, your personal directories. So in the long list you saw in the web portal, these were 2 entries. You have 25 gigabytes of disk space. That's maybe enough for you. For some people, especially people doing sequencing, that's peanuts. But it is very easy to get access to way more storage space. Once you're a member of what we call a virtual organization, so a group of people working typically in the same research group on the system, you can get access to hundreds of gigabytes or even terabytes. You just submit a request to get more access to more data. We approve the request, and about 1 hour later, you get all that extra disk space. And again, no charge, no bill coming afterwards. It's just a way for us to manage all the disk space that we have available in the system in a somewhat efficient way. When you're a member of a virtual organization, you get additional locations, the shared location with the other members of the virtual organization, and in there also your own subdirectory in both locations. So overall, you can get access to hundreds of gigabytes or even terabytes if needed. To check your current usage, you can go to the VSE account page. This is also where you created your VSE account. You can see things there of how much disk space is being used, how much quota storage space you have, what the percentage is, and also how many files you're using across all the disks, all the file systems that are available that you have access to. You can see this both for your own account. If you're in a VO and you're a VO moderator, you can also see how things are going in the VO. I think every VO member can see the overall view, so how much is being used. In this case, it's all 0, but I do have several terabytes of disk space here. And VO moderators can also check in a bit more detail, even per member, so per VSE account. And I think they also see names here of people to see how much disk space everybody in the virtual organization is using. So this is important, especially if you're starting to hit limits, and you may need to request more disk space. All right, so now it's time to look at the first complete job script. And if you've never run a job script before, this is a good starting point for the hands-on. Try to get this working in your account and try to get a result that makes sense. So what is this job script doing? It's asking for one core on one node. That's all we need. That's also the default if you don't specify this. And it's asking for 2 hours of wall time. Like, we want to make sure that we can finish this. It's actually going to finish in like 1 or under a minute even. But yeah, so 2 hours is going to be plenty. We're going to activate a relatively recent version of Python with some extra Python packages installed, like, well, NumPy is not in here, but some other things from the Python package index will be available here. We will copy an input file from the location where the job script was submitted from. So this is this environment variable. We will copy this to the temp dir location, so this temporary space where we can play around during the job. So this file is copied in there. We change to this directory, and then we run a small Python program which will open the file, read the file, count how many characters are in there, and then print that result into an output file. So this will say how many characters are in this input.txt file. We create an output.txt file from that. Now, the important thing to remember here is this file is located in this temporary directory. So if we don't copy this file, this directory is removed at the end, we lose the result. So that's why we need an extra line at the end. We copy the output file, in this case to our VSC data directory. And while we copy it, we also rename the file to include the job ID. So we have a new output file every time we run this job script. This is a very good one to try yourself. There's one important detail here. If you just copy paste this text into a job script and you run qsub on that job script, it will not work. Why not? There's one important thing to keep in mind here that is also needed for this job script to be successful. Balazs, you don't get to answer the question. Sorry? No, the bash is here on the top of the job script. So that's included in the job script. Yes, so this input file has to be there. If this file does not exist, this job script will still run, but it won't actually do anything useful. It will try to copy this job script, this input file. That's going to be an error, but it will just happily continue, go there, try to read the input file, which will not be there. Again, an error. It will actually create an output file, which is going to be empty, and then it will copy an empty output file. That's probably not what you want. Yeah, so keep that in mind when you try this, and that's why it's a good example. You need to create both the job script and the input file in the right place. All right, another example, and just to show you that job scripts are not that scary, it's always the same structure. We're going to run a multi-node MPI job. So we're going to use multiple nodes, multiple cores on different computers, and we're going to use MPI software to get all those cores to talk to each other, let's say. So how is this different? Well, we're asking for 2 nodes, 4 cores on each node, so 8 cores in total. This is gamed so it fits on the Donphan cluster, so you can easily try it there. We're asking for 2 hours of wall time, which is going to be plenty again. Here we load what's called a compiler toolchain. So this has an MPI library inside to run MPI software. We will also load our my MPI run tool to make it a bit easier to run MPI software, because when you start that software, it needs to know which computers to talk to and how many cores are available. All of that is actually automated for you through this my MPI run. So this is activating the software. We will change to the location where the job script was submitted from. So we go to the working directory, and in there we expect to find an MPI hello.c file, a C program, which is an MPI hello world, which you can download from this website, for example. We compile this program into a binary, and then we run the binary. And what will happen is from each of the 8 cores, you will get a hello. I'm core number 1. So you'll get 8 output lines in the output file of your job script. This is a good second example just to show you that it's not that different, not that scary. And what really changes is the software that you're using and what you're doing with that software. Any questions on this, on job scripts? Yes. Yes. Yeah, so this line is a comment. This will just be ignored. This is English text.
Yeah, but if read it?
No, if this has a hash in front, this is just text, and it will not do
Because
anything with it.
Reading it, and it was giving me error that you need to unload this module.
That's gonna be something.
If the line has a hash in front, it will just ignore it. Yeah. So maybe you change the JavaScript after submitting it. No.
I
Okay.
was saying, yeah.
Well,
Modules in your PowerShell. So when you log in, there is a script which will always run.
there's a
There
startup
might be
script.
some
Yeah.
problem, and this is why we recommend not to put anything in your PowerShell file, especially load modules, because when you change that file, you don't know what will happen because you submit a job, you have something in your PowerShell, you change it, submit another job, but the previous job is not started yet, so it might load the wrong module. So when you see that we don't have control, we don't see what you did there, because if you change it later, that we don't know what was the previous file. So we only recommend to put module loads commands only in your script, not into your PowerShell, because if it's in your PowerShell that you don't have control over, you might forget it.
No.
It's very hard.
This is a typical issue where you can send us an email. I'll explain at the end, or also for the hands-on this afternoon. If you can reproduce it, we can explain what's going on. But I'm sure if there's a hash in front, it's not executed. It's just text and it's ignored essentially.
It's even this is why it has a hash in front of it.
Yeah.
Because it's not executed. If you remove the hash, it will give you a syntax error. Let's call the directive and then the job script.
The Q sub command picks up on this, but yeah.
Specifically looks for that part, and then this is how it knows. But as a command, we do not execute it as a hash.
Yep.
You can also put a double hash, even the scheduler will not pick it.
Yep.
Just technique to avoid that. You can put things into the script which only the system will understand.
Any other questions on? Yes. Actually, yes. But we don't advertise this, but if you know Slurm already, you can just use the equivalent of the PBS lines, like the S batch, the S batch lines in Slurm, and do the translation yourself. As long as that works, fine. Right now, we're planning to move away from this old PBS syntax, and what we need to document, update our documentation, and actually get a bit more familiar ourselves as well. So right now, if you run into trouble, if you're running Slurm directly, you can ask the question. If it's an easy answer, we'll help you. But if it's complicated, or if we know we fixed this in PBS, then we're going to recommend you to use PBS. But if it works, yes, sure. There's no limitations there. You can write a Slurm job script and use sbatch to submit it, or use srun if that works. Fine. Yeah. Was another question?
Yes. Is this a primary way of using multiple GPUs simultaneously?
Well, yeah, a job script is one way, interactive is another way. So there's, yeah.
Because using
Depends on the software again. What you're using to access those multiple GPUs. It should actually work from an interactive job as well. So when your interactive job starts, it's really the same environment as your job script starts in. You're just working interactively.
If you start.
Yeah, I mean, it should work. No? I mean, you can select GPUs there, multiple GPUs. I cannot easily show that here because there's probably not multiple GPUs available. But if you start, let's say, a desktop session, you ask for 2 GPUs, you start a terminal in there and you run the NVIDIA SMI command to see, you'll see the 2 GPUs and you should be able to use them. Yeah.
So there is different the layer we can discuss later. So one is you have access for the GPU, other is your Jupyter node. You might have to do this here and there. So it's your software should be capable. So,
yeah.
And if you're running on DOM farm, there's only one available GPU, and it's also shared with all the other people.
Yeah.
So yeah, it also depends on
But again, this sounds like something we could look into this afternoon. And yeah. But there's no limitations. It should work interactively as well. Yes.
This job the script, Python script, the input data is copied temporarily before it runs.
There's actually no Python script here. It's a Python program, but I'm using the -C option.
I mean, just like
Yeah. If you have a Python script, you need a job script around it. You cannot submit the Python script itself. Yeah.
it is copied.
No.
Not necessarily. It depends on what you do. Here.
The question was that the script itself is stored, but whatever you pull from the script, if you call another script or use an input data or use a Python script in the submit script, that have to be there in the time when the job starts. The input data as well and the script as well. So you cannot do it that just you submit the job, you have the input.txt, you delete immediately after submitting the job, the input.txt, and then probably, I mean, fast enough, then the job will not start. Then it will say, oh, I don't find an input.txt. It's just the script itself, purely the script. What's inside, you refer to it, it must be there at the time job script starts to run.
Yep.
And during the run. So
Maybe it's helpful if I just show this hands-on. So I'll go through the slides here. I didn't mention it in the beginning, but if you go through the training page and you scroll to the very bottom, and this just keeps popping up, you'll find the slides here in course material. And what I will do is scrolling is horribly slow. Yeah, all right. I will actually copy this single core job script. So this is what needs to go into the job script itself. I'll copy this and let's see if I can shoot myself in the foot here. Let's go here to my data directory, which I think is a bit less busy. Actually, I'll make a new directory, HPC intro, and I've probably done this before, so I'll add a date, September 25. It is, I think. So this should pop up. Come on, I should have cleaned up my account. So what I want to do is, I've copied this text here. I'll put this in a job script and show you how to submit it. Come on, computer. Yeah, now I can. Yes, it did. Why? No, it doesn't like me. Let's see if this works. This is a typical user experience.
It was without the dash.
Was it?
I think so.
Oh. Oh, yeah, I'm there. Yeah, I was waiting, but it's there. Okay, so what I want to do is I'm now in this empty directory, this new directory.
Now it's in September 2. No, that one also does not exist.
Things are supposed to work when I do demos. Okay.
Arrived.
Be like such a user. All right, so a job.sh file, a new file. I'll edit it and paste the contents here, which doesn't have the nice colors, but it has all the parts, the resources, the loading of the module, copying of the file, going to the directory and copying back the output file. So I'll save this. And then the next step is to actually submit this. Let me refresh. Yeah, so this file is there. Now I can do two things. I can go to the terminal here and then navigate to this directory, or I can just click open in terminal and I'll be in the right directory from the start. Right. Now I'm in Linux mode, so I need to know these commands to run. I can do ls. I can do ls. I can check what's in the file by running the cat command on the file. So this looks good. And now I'll just do the naive thing and, well, except that I will not use the default cluster. So if you run module list, you'll see it's talking to the Doduo cluster by default. I'll change this to the Donphan cluster because there my job should be starting quickly. Yeah, I'll need to check the interactive jobs. Let's do that actually here. qstat. Do I still have these things running? So these are the interactive dashboard jobs. I'll get rid of those because I don't need them anymore. qdel this, qdel that. So these are the job IDs that I'm using to remove these jobs. So that means they should be ending quite soon. And now I have breathing room. I have cores available to run my new job script here. I'll run qsub job.sh. And if I'm quick enough for run qstat, I will see that it's in state running. So there's no waiting time on Donphan. That's very good. And after a while, it will go to status C for completed. So this was only 7 seconds. Very good. If I run ls again, I'll have 2 new output files. A .o file for regular output, a .e file for errors and warnings. And with ls-l, I can see how big these files are. So the output file is empty. Okay, the error file is not empty. That's already a red flag, right? So this looks like something has gone wrong here. I can check what this file has, and this has exactly what we expect. I was copying a file that doesn't exist, so no such file. Python was trying to read this file, it says file not found error, so the error here is pretty clear. I can actually do the same thing here. If I refresh this, I can also inspect the file here in the web portal. Okay, so the one thing I need to fix, go back here, is I need one more file, input.txt. And let's put something in there. Hello, Balash. Save the file. And now the big question is, how many characters does this file have? So we now have an input.txt file right next to the job script. And remember, one line in the job script says, go to where the job was submitted from. So that's this directory. If I now qsub this again, I should get a better result. Again, it will still only take about 7 seconds to complete because this is not actually doing even 6 seconds. I now run ls again. This is the old one. This is the new one. The error file is now empty, but now the output file is also empty. Where does the result go? Let me show the script again. So why am I not getting any output in my .o file? Yeah, so there's none of these commands actually generate output. Well, this one does, but we capture the output into a file, and then we copy that file to somewhere else. So if I go to my data directory, I'll do it here because in the web portal it's going to be very slow. So I can go to VSC data. I can run ls here and just sort the files according to most recently updated. And this file here is our output file. So I can check what's in here. Oh, and by the way, tab completion is one very interesting thing. You can start typing. You hit the tab key on your keyboard. If you wonder what tab is for, it's for this output. And it will, if you double tap, it will show you how it can complete things. So the one that we want is the 2001. No, the 2021. 38. Yeah, this is the job ID that we had. So there's 12 characters in that hello Balash file. So that's why we're getting no output in the .o file. Is this helpful to see this workflow a bit? It's always the same workflow: submitting, checking, QStat. How are my jobs doing? Everything here is complete. But I like QStat minus AN a bit more. That's an alternative view. It also shows you on which node the job is running. Sometimes that's useful. How much time has elapsed, how much time you requested, you get a bit more information here. I forgot the most important part. That's coming up. That's coming up in the slide. Yeah. All right. So that's coming up here as well. Output files are running ahead a bit. Just to almost wrap up, I think we then have one more part for you. It's Q2. So this. Yeah, I still have this part. So 2 small examples next to the job script, just to go back to the OpenMP, the multi-core software, and the MPI, the multi-node software. This is how it looks like if you're actually coding that type of software. So this is C code, and you don't need to fully understand this. But when you're having an OpenMP program, you have multiple threads that are run, and each of the threads can ask, what is my thread number? What are the total number of threads? And based on that, they can figure out what part of the work they are going to do. If you have an OpenMP program, you need to compile it with a compiler, with a flag like -f OpenMP. Then you get a binary, and you just run that binary in your job script. If you have an MPI program, it's a little bit different. Of course, the code is different. But also here, you can get a unique number for each of the MPI ranks, each of the processes, which may be running on different computers. You can ask how many ranks, how many processes are there in total. And based on that, again, you can decide what to do. In this case, just print a line. But you also need to do this init and finalize step to set things up and tear things down again nicely. Here also, you need to compile that software. And to run it, you need a launcher like MPI run, which will go and talk to each of the computers and say, you guys need to start this binary. And then the binary start talking to each other through this MPI init and all these MPI statements in the code. We have a wrapper for this, the myMPI run. Makes it a bit easier. You don't have to tell it how many cores to use. It just checks the job environment, how many cores are available, and it just uses all of them by default. So myMPI run is definitely recommended. Job output files, I showed this actually interactively. For every job script you submit, there will be a .o and a .e file. You can actually join them if you want to as well. They will be submitted or created in the location where the job was submitted from. And also in your job script, you can capture output, also capture errors separately if you want to, and create additional job scripts. Also, this is well covered in the Linux tutorial that we have. This is all new to you. And of course, the software that you're using, maybe a Python script or maybe MATLAB or something else, can even create additional output files. So this is, of course, very software specific. To submit jobs, you pick a cluster. Donfun is a good one to start with. You qsub the job script. You get a job ID back. With qstat, you can check the status of the job. How long is it running? Is it actually running? And so on. And if you made a mistake while the job is running, you realize, oh crap, this is not doing useful work. You can just queue down the job and the resources are released for something else. And then job scheduling. This is a question we often get, when will my job start? Well, we don't know either because we cannot predict the future. It depends on how busy the cluster is, what other people are doing, how many people are actively submitting jobs at that point, how many calculations they have been doing in the past. So we try to balance the usage across all users, which is impossible because if you are not submitting jobs, then you're not getting compute time, of course. But we aim to keep things fair, essentially. And if you've been using a lot of compute time recently, you'll get a lower priority compared to people who are new on the system. Also, the more resources you request, typically, the longer you will have to wait because a gap has to be available in the system that's bigger. And as your job is waiting in the queue, gradually it will climb to the top and eventually gets executed. We also have some user limits in place that make sure that one person cannot fill an entire cluster. So it's a big balance of things, and it depends on what everybody else is doing. So it's impossible to predict. And also, typically, the amount of wall time you ask for, you're not going to fully use this. So most jobs finish before the time that they asked for. So all of a sudden a gap opens up and then your job can maybe jump in. So it's really impossible to predict. One particular type of job we see is very small jobs, very often single core tasks that maybe run minutes or even seconds each, but you need like 1 million of those. That's a typical use case we see. If you have a use case like this, don't go and create 1 million job scripts and submit all of them manually. Don't do any boring, mundane stuff like this. There's tools that can help you. You can use array jobs. You can use additional tools like GNU Parallel or Worker, and they're well documented. So if you have use cases where you get many very small jobs, there's tools that can help you organize this and essentially submit one big job and then process all of these small tasks in there. That's just important to know. That's a use case we see quite often. Yeah.
Okay. So yeah, Kenneth showed you earlier the amount of software that we have installed, but yeah, compared to the software that is out there, it's still very little, and especially for Python packages, yeah, there's a lot of packages, and yeah, we don't have enough manpower to install every single Python package that is out there for all the users that are there. But we do support that you have your own Python virtual environments on the machine, and you can also leverage the software that is already there. So if you, for instance, are using a small package that is built that needs PyTorch, you can use the PyTorch that is available on our system and yeah, build on top. And so this is a workflow, but the thing is that yeah, this will, if you're using it with the modules, it will be specific to the cluster, so it might not be possible. So if you're, for instance, building this environment on the login nodes, you will only be able to use it on Dodo. So if you want to use it also on DOMFAN or one of the GPU clusters, you'll have to first build the virtual environment on those systems to be able to use those. And yeah, so, and you also, if you make that Python virtual environment with those modules, you have to make sure that those modules are always loaded. But to make this whole process easier for the user, and so that they don't have to worry, oh, will this Python virtual environment still work on the cluster? What are the modules? We have built a tool for you, which, or one of the students who did an internship with us a couple summers ago, he built this tool. It's VSCVenv, and so what this tool does, you have a modules.txt file in which you can add all the modules that you need in your Python virtual environment. You can add a requirements.txt file which will have all the packages that you want to build on top of those modules. And so when you load this VSCVenv, it will create a Python virtual environment for you. It will make sure that it will run on the cluster that you want it to run. And every time you change something to the modules.txt file or the requirements file, it will also update that virtual environment. So if there are changes, it will also do that for you. But if the virtual environment stays the same, then the tool will just use the Python virtual environment that it made in the last session. Okay. There's also documentation on this. And here is an example. So you have a modules file with SciPy bundle and pillow, and then you build, for instance, beautiful soup on top of it. So what it will do, so you will have just to load a module named VSCVenv, source VSCVenv, activate requirements with the requirements file and the modules file, and then it will do everything for you in the background. And so you can just add this to your job script where you're going to use it or in an interactive session. For installations on our system, for the central installations, we are using EasyBuild at the moment. We get a lot of requests from users, and in some stuff we put a lot of time. So for some stuff you might have to wait a long time. At the moment, we also try to be more open about how much time we're putting into it and how much effort goes into it. So when you're requesting software and it's installed, you also get a message on how much time and money went into doing this, but there will be no bill, so don't worry. It's just an information for you guys. And yeah, so EasyBuild was also originally developed here at Ghent University, and now it's a tool that's being used by over the whole world by experts in HPC. So yeah. So if you, for instance, want to also deep and be able to install your own software centrally, install your own software, you can also look into this tool to get more information on it, and you can find the documentation here. And because because EasyBuild was here, and because UGent is central in the software ecosystem for HPC in Europe and the world, we became a part of the multi-xScale project. I was also hired on that one, and within this project, we are creating the European Environment for Scientific Software installation. It's a shared repository of optimized scientific software. And the thing is, it's a uniform way of providing software to the users. So as you have the modules on our system, it also uses that as a module system. The difference, it works on any Linux distribution, and so that means that the software stack will be the same wherever you go. So if you want to install this on your laptop, if you have Linux running, you can have the same software on your laptop, on your computer, or in the cloud. It's also optimized for CPU architecture, so it will also guarantee performance, and the software will perform as good as possible on your specific system. And so at the moment, it's already available on 50 systems across Europe, but also here at UGent. So if you want to start, this is an overview of how, a high-level overview of how easy is put together. So we have the host operating system that's underneath that we're completely free of. Then we have a file system layer and a compatibility layer. All the software in the in Easy is built on top of this compatibility layer, which makes it portable to any system you want it to run on. And so then you have all the applications within Easy can run on any system. And we already have about 500 different software packages in the repository, and about 1,000 modules in total. It's at the moment we have software compiled for FOSS 2023A and FOSS 2023B, and we're also starting to build 2024A in a newer version of Easy. And if you want to find the full overview of software that is installed there, you can find the documentation. And so the reason that we're doing this is we want to, that we're highlighting this right now is that we want to inform everybody that this is now also available on on our cluster here at UGent, so that if you start using it maybe on your laptop, you can also use it on the clusters. So it's a different software stack that is separate now from our central software stack that you can also use. This script you can also run. You can also find it on the cluster already. So if you copy this file, if you copy this file, then you will be able to run it yourself. And so okay. Any question? If you have questions or want to get help, please contact us via hpc.ugent.be. Please give as much information as you can. If you just say to us, I have a problem, we will not be able to help you. So try to give your login ID, give the job ID, give screenshots, copy parts of the output files, input files, so that we have as much context as possible on the problem that you're encountering, so that we can help you. If you have questions and problems, sometimes you might have to wait in the queue and be a little bit patient. Just like you have to wait for a job to start, sometimes you have to wait for us to get to your problem. We get about 50 to 100 tickets a week, and at the moment we're with 4 to 5 people, so it sometimes might get, but it might take some time, but we'll help you out eventually. And if you notice that your ticket hasn't been handled in like a couple of weeks, feel free to just send us a reminder, and then we'll get to it when we get to it. Then we also had best practices now already a little time ago at the VSC User Day in 2024. This also had like best practices on how to use Linux environments, how to use the supercomputer. So if you want to learn more about the supercomputer and what the best way to use it is, then feel free to find this presentation. The slides are online, and I think there's also a recording, so if you can still revisit that. Then the agenda for this afternoon. So now there's lunch in the back for sandwiches, and around 1 we'll then leave to the data center for the tour. And then once we're back, we'll have a hands-on session for the people that are here. Okay. Any more questions?
Yeah, we can take a couple more questions now before we have lunch. Also, the people online, if you have any questions, feel free to post them in the chat and we'll try to answer them. Just one more thing on the VSC User Day, there's another one coming up this year as well in October. So if you check the VS Centrum website, you'll find the User Day as well. This typically happens in Brussels, but there you can also meet researchers from Leuven, from Brussels, from Antwerp who are using the VSC systems if you're interested in that. Yes, any questions? Yes. Yeah. So, okay, you can definitely use Conda in your own account to install Conda environments yourself. There's a couple of caveats there. Conda is very aggressive in terms of changing things in your account, in your startup script, in your home directory, creating lots of files there. So sometimes it's not a very good experience. But if you learn how to deal with these issues, it's definitely fine. And you can take matters into your own hands, create your own Conda environments. To share Conda environments with other people, we don't have a location on the system where you can put your Conda environment and then tell everybody else it's there. But you can give them instructions on how to install the Conda environment in their account. That's definitely possible. Yep.
Make recipe, you can share recipe with other people, and then they can just.
Yep. But we don't have a location where you can share data with everybody on the system.
And in general, it's also not advisable to share the same Conda environment between different users, because Conda, you will see strange errors with Conda if you try that. So it's best to just share the recipe that they install it themselves.
Example, the job, instead of do it like with module load, stuff like that, or how?
Then you just activate the Conda environment. Yeah, so instead of module load, just do Conda activate or source activate, whatever. And that sets up the Conda environment. And then the lines after that, you can assume they have access to the software from that environment.
It's not recommended. The reason is because you don't know what will happen. So what we ask that you don't install anything in your chassis, but you have to activate everything from your job script. It's help us to also we have to debug it or if there's a problem with it. Because we actually know what kind of Conda environment you use, how do you use this kind of thing. So that is much better way than you just put in chassis and then you already end up in the Conda environment. So why is it also important? Because Conda is, as Kenneth mentioned, it can be very aggressive. Also, there are situations when a Conda environment can actually interfere with the system files. So there are system commands which will not work after you activated the Conda. Let's say, consider that you log in your account, the Conda is activated in the chassis, you try to issue some commands and it will not work. It happens in few cases, but we had some examples.
Yeah, for instance, Globus, there was a person who could not use Globus anymore because she had Conda in her chassis.
If you want to access the shares, you can shares that will not work. also depends on what is in the Conda environment, but it's very easy to happen that they make a Conda environment or accessing to shares, the you can shares will not work from there.
So in terms of software, there's the central module system. There's tooling to help you out with Python virtual environments. There's easy. You can use Conda yourself. You can use container images yourself as well through Apptainer. We didn't mention that. There's a whole variety of options for installing the software that you need in your account. Yeah. We're not forcing anything. And as long as whatever you're trying is working, that's fine. There's no restrictions in terms of what you can do. Well, there are. You don't get root access. You don't get administrator access to install stuff system-wide. But as long as you can do it only in your own account, fine. Yeah.
Sorry.
Sure.
When I set up session, just install the Python 3.9. If I need something else, I should do it manually or.
No, so you can load a module like I showed. Or is this?
Itself, it's a very basic module, not so many things in it. But we have that extra module which contains lots of pre-installed libraries. For example, the SciPy bundle.
So the Python you're seeing is probably this one. Yeah. If you load a module that gives you another Python version, you'll see a newer Python in a different location and maybe a bit more Python packages activated. So this is the type of thing you want to look into. Yeah. More questions? There was a question online if there's an online session for the hands-on. No, that would be too difficult to organize. So for the hands-on, people are expected to start with examples or start with their own research software problem. We will walk around and help and answer questions, but that's not feasible online. But if people want to do this themselves, try the examples, you can send us an email, hpc@ugent.be, and we're more than happy to answer your questions there as well. Yep.
Then if you have for the people, if you have a problem, just ask us on the help desk. And you mention that each example. We can also answer that one. Of course, it's a bit slower, but
Or come to the hands-on next time. Yep.
I think that's the question there.
Is there? Yes. Yes.
And shares?
Yes. Shares? Yes. Yeah, I think so.
I think
Yeah, I'm pretty sure. Check the documentation. Globus is mentioned in our documentation. But yes, I think you can transfer from shares to your VSC account or the other way around. Yes. Okay, if there's no more questions, I'm hungry. I'm sure other people are as well. Let's stop the recording here. Thank you for the people online for joining us. We'll have lunch now, and let's aim to be ready by 1 p.m. to go to the data center. You can leave all your stuff in here in the room. I think, Balázs, are you going to stay here when we do the tour? Well, is anyone going to stay here who doesn't want to join the tour? Okay, if everybody will join, we'll go find the key and we will lock up, so you can keep your stuff here. Or Bart will maybe be here. Two is fine. But let's do lunch first. So lunch in the back. And we'll be around also if you have any questions.